Good morning, good afternoon, and good evening to all of you that are attending this conference today from different parts of the world. While I do understand last year has been quite difficult for many of us, I really hope that you and your families are doing well during these troubled times. Lucia Schuler, myself, Samaya Jamil, and Nicholas Koo wrote this paper sometime last year after researching applications of AI in enhancing autoscaling in serverless environments, namely Knative. And what we'll cover in today's talk is basically our motivation behind the paper, the experimental infrastructure setup that we had in place to do our baseline experiments on, which then confirmed that tweaking certain parameters in Knative actually do have a significant impact on the performance of the application. We'll also talk about the performance impact of this particular application when we used AI to tweak those certain parameters. And at the end, we'd like to summarize the findings. Now, before we deep dive into the motivation behind this paper, I would like to quickly touch base on the serverless platform that this paper is based on, which is Knative. For those of you who do not know what Knative is, it's basically an open source Kubernetes-based platform wherein a developer can deploy and manage serverless workload. Now, the most important feature of Knative is its autoscaling feature, wherein an application's replicas can be scaled up or scaled down depending on the incoming demand. It can also be scaled down to a 0 if there is no traffic on the application. And Knative is using many settings to achieve this desired effect. And one of those settings is container concurrency, which is basically the number of simultaneous requests that can be processed by each and every replica of an application at a given time. Now, a user can set two settings, which is the soft limit and a hard limit. To give you an example, if there is a burst of incoming requests, the soft limit here that the user has specified can be exceeded. But if the container concurrency limit is already at the hard limit, any new incoming requests will be buffered and can only be processed after enough capacity has been freed up. For the bounds of this paper, we are going to focus on the hard limit. And to give you an example of how this would mean or what this means for our incoming requests, let's take 5 simultaneous incoming requests. If a user has set a container concurrency of 10, we would only need 1 replica to service these 5 incoming requests. If there are 59 simultaneous incoming requests, Knative would spin up 6 replicas. And for 467 simultaneous requests, Knative would spin up 47 replicas. And now coming to the motivation. We wanted to evaluate if this container concurrency setting has any impact on the performance of an application. And if it does, can we leverage AI to keep tweaking the setting in order to get better performance results based on changing application code, the infrastructure location where the code is deployed, the load on the infrastructure at that time of the day? We basically wanted to help the users to just run their applications efficiently without having to worry about this setting causing any performance degradation.
So to measure the impact of different concurrency settings on the performance, we then designed the following architecture consisting of 3 components. So we have 1 agent coordinating the tests, 1 smaller client cluster to simulate the user requests, and 1 bigger service cluster on which we have Knative installed and also our sample application service. And with this experimental setup, we then run lots of different tests with varying concurrency limit configurations. And one test was always designed to test for one specific workload profile and to measure the performance indicators at different concurrency limits. To generate the load, we used the Gida load testing tool as it allows to send a constant request rate. To simulate different kind of workloads synthetically, we use the Autoscale Go application as it allows to pass certain parameters with the request to either allocate a certain amount of memory, to calculate prime numbers, to create CPU load, or to pause the request for a certain amount of time. So in total, we run almost 20 different workload tests. Coming now to the results, we saw quite a lot of variation in the performance indicators across different concurrency settings and workloads. So, for example, when we take a deep dive now in workload test 10, which is defined by the here displayed setting of parameters, we can now see the performance indicators at different concurrency configuration on the x-axis. In red, we have the curve for the average throughput values. In blue, we have the mean latency, and in the screenish color, we also included the 95th percentile tail latency. And what we found out here for this workload test, for example, is that higher concurrency is not always better. So for this workload, we have the highest throughput values at a concurrency setting of 10. And at the same time, we also have the lowest latency values at a concurrency setting of 10 as well. However, when looking at a different workload test, so for example, workload test 7, which is defined by another set of parameters, so in this case, a higher prime parameter and additionally a sleep parameter is given with the request, we can see a completely different picture in the performance indicators. So when looking at this graph, we don't see the highest throughput or lowest latency values anymore at a concurrency level of 10. Instead, we find the best performance at a concurrency setting of 70 for this specific workload case. So all in all, our baseline experiment showed that for different workloads defined through a different set of parameters, we have different concurrency setting that results in the highest performance or the highest throughput or lowest latency. And when we summarize the key results here, we could see that the smallest possible concurrency of 10 is the most common configuration that results in the best performance across all three metrics. For workloads that consume memory exclusively or additionally lower CPU, they perform better with fewer parallel requests per pod instance. However, when we pause requests for a certain amount in time, they perform better when having a higher concurrency chosen. Additionally, we can see an inverse behavior of the measures within the tests. So we have a high throughput together with a low latency, and this allows us for the further test to only focus on one metrics, because when optimizing, for example, for throughput, we also optimize for latency. To summarize the main findings of this baseline experiment, we can say that a variation of the concurrency limit can definitely influence the performance of a workload, which then further motivates part 2 of our experiments, where we want to apply reinforcement learning to improve this concurrency configuration automatically. So before introducing part 2 of our experiments, we want to have a quick look at the existing literature, since there has been already considerable research done into techniques for optimizing autoscaling, however, mainly in the field for virtual machine provisioning. So we analyzed the different approaches in the context of our use cases and evaluated if they are applicable to our problem statement. A common approach here is scaling based on a predefined threshold. This is relatively easy to implement, but on the other hand, it requires a detailed understanding of the workload characteristics, and of course, there's no adaptation to different workloads. A second approach is application profiling. Here, the workloads are categorized into different classes, and their sweet spot of scaling is identified. Of course, here the quality is dependent on the number and variety of workload classes defined, and it's hardly scalable for a large variety. A third approach is queuing theory. Here we have a model that is created simulating the system dynamics and that calculates the optimal utilization rates. This is a very static approach, and here a change in application or in the workload would always require a recalculation of the whole model itself. So we also had a look in the fourth approach, which is reinforcement learning, and it's basically a trial and error process where an agent learns an effective scaling policy on the fly. And this was very promising to our use case, since here we have no knowledge required about the application in advance, and we can learn the best concurrency setting online during the workload execution. So how can this advantage be achieved? What is reinforcement learning? Well, basically, reinforcement learning describes a set of methods in which an agent independently learns a certain strategy within a certain environment. So the overall goal of the agent is always to maximize its total reward over a large number of iterations. And in each iteration, the agent would start in its environment in a specific state, would then choose a certain action, perform this action, and this action would then transitions the agent to the next state. And depending if this was beneficial or not, the agent either gets a negative or positive reward. So over the course of many iterations, the agent learns which actions and which state define a good strategy that maximize the return without having any prior knowledge about the system dynamics in advance. And this is very beneficial in our use case, since we can apply it to unknown workloads during runtime. The specific reinforcement learning algorithm we choose is Q-learning, which is a model-free reinforcement learning algorithm. And in here, the agent always tries to learn the so-called Q function or Q values for individual state action combinations. And these are then stored in the so-called Q table, which the agent is populating. So at the beginning, the agent is doing a lot of exploration and populating the Q table, and at the end of the course of iterations, the agent tends to less explore and rather choose the action in a specific state where the agent knows that this is beneficial to maximize the overall return. So translating this to our use case, in the second part of our experiments, the Q-learning experiments, we basically used the same experimental setup, but we additionally implemented a Q-learning logic in the agent so that the system can learn by itself to test different concurrency limits and learns over time a good scaling policy. So in our setup, the agent can choose by either decreasing, maintaining, or increasing the concurrency limit, the concurrency setting. And the state space is defined by three variables: concurrency limit, average CPU, and average memory utilization. We further also defined a very simple reward function, the ratio of the current throughput and the reference value. And here we say the reference value is always the highest throughput to date. Can be seen like a target SLA. So in the second part of our experiments, we let the system choose and test different concurrency settings at the beginning, so doing a lot of exploration. And over the course of iteration, we decreased the probability of just choosing random exploration and instead more oftenly choosing the action that would lead to the best concurrency or the best performance indicators. Looking at the results of our Q-learning experiments, we can say that the agent can learn within a limited time a scaling policy that improves the performance in terms of throughput. So when we now have a deep dive or a closer look at exactly the same workload tests that we looked at in baseline experiments, we see now the results for workload test 10. On the x-axis, we have the curse of iterations. On the y-axis, we have in blue the concurrency limit, and in red the throughput for each iteration. In this graph, we can see at the beginning that the agent is performing a lot of randomly exploring the action space. So the agent tests a lot of different actions and increases, for example, the concurrency limit of up to 310, and then also goes down to a concurrency limit of 10. Of course, the throughput also varies with choosing different concurrency limits. Over the course of iteration, the agent tends to less doing random exploration and rather choose the action that would lead or optimize the performance in terms of throughput. So at approximately 350 iterations, the scaling converges to one specific concurrency limit. In this case, it's a concurrency limit of 10, which also optimizes the throughput for this workload profile. When we look at the results of a different workload test, so for example, workload test 7, we see a completely different picture in the learning progress itself. But also in this case, the agent learns within a limited time a certain scaling policy and narrows down the concurrency options. So in this case, we can see that there's much more variation in the throughput values in red, and also the range in which the throughput values lies is much smaller, which makes it much more difficult for the agent, for the system to identify which specific concurrency limit yields the highest throughput or the best performance. And that's a reason why we can also see much more balancing and variation in setting the concurrency limits. However, after approximately 380 iterations in this case, the scaling configuration stabilizes and is alternating only between 1, 2, or 3 different concurrency limits at the end. To evaluate if the setting the agent learned by itself is really beneficial, we compared the average throughput over the iterations of the Q-learning test with the average throughput of the same workload but using a constant setting. And what we can see here now, exemplarily shown for the both workload tests that we went into more detail before, is that at the beginning, the constant setting is better since our Q-learning model is randomly exploring a lot of concurrency settings that are also not very beneficial. However, over the course of many iterations in both workload tests, our Q-learning model outperforms the performance retrieved by using a constant concurrency setting. So, and this brings me now to the summary and the final discussion on our experiments. First, I'd like to point out some limitations of our experiments. So we used synthetic workloads defined through one application and passing different parameters with the requests. So all the conclusions we made on our result are of course based on these specific synthetic workloads we used and are not valid for all different kind of workloads. However, they give a clear indication that there is some improvement through different concurrency setting based on the workload profile. Second, we used a rather simplified reward function, as already pointed out before. This also definitely opens some space or has some more potential for further improvement to even improve the efficiency of the model and maybe even learn good concurrency scaling much faster than we did now in our experiments. To summarize the results, first we can say that the concurrency setting definitely has an impact on the performance. Depending on the workload, this can make up to several seconds in latency, which might also have a big impact on the user experiments for these serverless applications. Second, we could show that our reinforcement learning component is able to learn the optimal concurrency or an optimal concurrency within a limited time. And looking at the throughput and latency numbers, we could show that our dynamic concurrency learning, concurrency configuration is also outperforming a constant concurrency setting. So thank you very much to listening to our presentation. I hope you enjoyed it, and I hope it gave you, or it might give you, an additional input on how to combine reinforcement learning and serverless. In case you have any question, please feel free to reach out to us. We also included the key references on the following slide and the links to our paper and the conference either on the bottom of this page or at the very first page of our presentation. Thanks a lot.